There's no participants. You know the presenters just out? Yeah. Some just This one's mine. I have to watch the.
Do I have the fourth speaker of the session here? No, not the first, the fourth paper. Yuan from UIUC.
Yes, thank you. Is something coming up?
It takes a second.
I see. So. Great. Tell me if I start. All right. Mm-hmm.
All right, welcome everyone to Optimization of Tensor Program session. And for the first speaker, we have Yifan Zhao, a fifth year PhD student from UIUC, and he'll be talking about Felix.
Thank you for the introduction. Hello, everyone. I'm Yifan Zhao from Illinois. Today, I'm very excited to share with you our work, Felix, and tell you how we better optimize tensor programs using gradient descent. Let's say you need to run some DN, maybe in your app. You click on the launch button. Oops, the DN is taking way too long to run. Happens all the time. So you go to tensor compilers, a number of tools designed exactly to speed up your DNs. To a tensor compiler, your DNA is a graph made of compute kernels. And to optimize the DNA is to transform the kernels so that they run faster. And that is the job of an optimization schedule. Let me give you a concrete example. So this is a matrix multiplication, which takes two matrices, A and B, and outputs C. If you just write down the mathematical by the mathematical definition, the way it computes is really straightforward. It just goes through the first row, and then the second row, and so on. Here, this is a schedule. A schedule is a list of transformation steps that can be applied one by one to the original program to previous program. And here we are changing the computation order so that instead of computing a whole row at a time, we are doing this, which can be good for performance because cache locality. In modern tensor compilers, there are typically tens, dozens of ways to reschedule the program. And the combination of them can be literally billions of ways to rewrite your kernel. So to actually find a high performance kernel, existing tensor compilers run a discrete search for it. It goes a bit like this. You sample some kernel, some schedule, that's your starting point. And then you check out its performance, which probably is not going to be very good. So then you take your initial point to, yes, that is intentional. Yes, just one moment. Get to a point, yes. You mutate the kernel to create some more kernels. And then you check out their performance. And then you repeat this process. And you go into various kinds of directions. And hopefully that gives you something good. I think this kind of search quite looks like a walk in a maybe dark forest. Because you are feeling your way around, this kind of slow, discrete search can often take hours or even days. So how can we do better? Well, if you look back to the search we just did, you realize that maybe there looks like an outline. There may be a shape to the underlying search space. I just wish we can look at the shape directly. And then if we have that available instead of the discrete search, we can do this. Just take the path down the hill to arrive at the fast kernel we want. And that is Felix. We use gradient descent on a landscape of kernels, starting from slow ones and descends to arrive at fast kernels. Of course, this is not going to happen automatically. It requires gradient information to be available at every point of schedule in your search space. So to explain how we do that, let me take one step back and show you what happens in one step in existing discrete search. You have a schedule, you want to evaluate that. So what happens now is you apply the schedule because it's a list of transformations to the original program to give a transformed program. And then from that program, you extract a number of program features which are used to predict the performance of the transformed program, therefore the schedule. The program features here are something like the number of float operations, the size of the buffers, and reduce distance of the buffers. And you can think of that as feature engineering for the performance predictor. There's something similar in Felix, but that is not enough, because in addition to this, we now want gradient. The last part of the pipeline is, in Felix, is a feed-forward network for the performance prediction, and that part is easy to make differentiable because you can run backprop on the feed-forward network. However, the other two parts are much, much harder to make differentiable, because now you have to change entire program transformation and analysis pipeline in your compiler to make the gradient happen. So to make that happen, we swap out three key things in Felix: schedule, symbolic schedule; program, symbolic programs; features, symbolic features. And now that becomes differentiable. But now I will explain what each part means. Okay, so first thing, what is a symbolic schedule? Let's take the same example, MATMO as an input. A symbolic schedule looks like a schedule, but now instead of the concrete parameters for program transformation, now you have variables. So like N0 here is used for the new size of the loop that you want to tile. Because we have introduced the variables, we also have constraints on these ranges. We keep them in mind. Felix keeps them in mind. And then Felix relaxes the variables into real valued variables. And these two things, steps, constraints together, that's the symbolic variable, symbolic schedule in Felix. And then you just apply the steps in the symbolic schedule onto the original program, and that produces a new program which we call symbolic program, because the variable we introduced in the schedule will now appear in your program. And that is useful because now when you extract the program features, your features become expressions of these variables. Last thing, so we have expressions which are not yet differentiable, but we are close. So there is a function smoother path in Felix that will transform the expressions into approximate and differentiable counterparts, like smooth if, smooth max. Now these operators are differentiable. So that enables you to have gradient for the features. What happens now is straightforward. In Felix, you sample some initial points, schedules, but here it means you sample some initial values for your variables, and then you do that pipeline with 3 steps of symbolic components, and then you get a gradient. And you feed the program feature values to the feed-forward network to predict the latency of the schedule, and that is also easily differentiable as we have seen. So now you have end-to-end gradient. What can happen now is gradient descent. You push your initial set of variable values in the direction that minimizes the predicted latency, and you can do multiple iterations and so on. And now, after you have done a few iterations, you have a history of these variable values. Now, what has to happen as a last step is you select the best among them based on the estimated performance. And then you do rounding to round the real numbers back to integers. You substitute them into the schedule, symbolic schedule to get concrete schedule. And then you double check if they are all valid schedules. And then last thing, you take these valid schedules, you measure them on the actual hardware that gives you the optimized program. Let me show you the results we have. We evaluate Felix on Llama, large language model, vision transformer, and as well as a number of CNNs, convolutional neural networks. We run Felix for 3 GPU, 3 hardware setups. And we compare Felix against PyTorch 2.0, TensorFlow, TensorRT. These are deep learning frameworks, as well as TVM answer, that is a tensor compiler with auto-tuning capability. On A5,000, we observe that Felix can produce 1.5 times faster DNNs on average, and up to 5.4 times in just 7 minutes of tuning time. So that means your tuning time is now minutes instead of hours or even days. Oh, by the way, so the y-axis here is the normalized performance, which means the performance of each DNN is normalized to the best one being 1. So here we are actually comparing against the best among these 3 frameworks, TensorFlow, TensorRT, and PyTorch. Now, comparing to answer, we achieve much faster convergence. The way we measure how fast we converge against answer compared to answer is this. So we take the best performance ever achieved by both frameworks, and then we take 95% of that performance, and that will intersect with both lines. That gives you how much time it takes to get to the 95% of performance level. And that is 2.4 times faster in Felix than answer on average. And we reach similar final performance because both Felix and answer are based on TVM and set up to use the same size of search space. You can see the same trend persists on all the 6 networks we are evaluating on. Okay, to wrap up what Felix is in a few sentences, we found that discrete search for schedule is slow, often taking hours or even days. So we came up with the idea that we want to make the search differentiable, and that is Felix. We evaluate Felix, and Felix tuning turns out to be fast and also generates high performance DNNs. That concludes my talk. Thank you. I will take our questions.
Hi, thanks for the great talk. This is Zhao from Carnegie Mellon. So my question, can you elaborate more on the smoother part? Because I'm asking because sometimes if you change the value of n by 1, that may double your cost, such as, originally you can write down a single tensor core, but right now you have to launch as, by increasing n by 1, you have to launch them as 2 separate tensor core instructions. And so how do you handle this case in your smoother?
I see. So smoother, you're talking about the part that changes the program features into the continuous approximate parts, right? Like this one here. So I think that may be a different thing from n going from 1 to 2, because well, like this is approximate, it will state with the original function quite closely. Yeah.
Quincy from University of Maryland. So how do you do batch optimization? Because you basically convert this into an optimization problem, right? Is it a single instance you initialize and then you do optimization, or is it batched process?
Oh, that's a very good question. So we do start from multiple points and we gradient descent on them all at the same time, exactly to avoid being stuck into local minima. So
it's all parallel and then you start with one at the end. So you don't need to do any backtrace or restart.
Yes, that's right.
Okay, all right. Thank you.
Hi, nice work. Arvin from Simon Fraser. It seemed from your plot that getting the last 5% seems to take longer with your system rather than answer. Am I reading that correct? And can you...
Like this?
Yeah, can you show the next one?
Oh, right.
Yeah, so it seems like getting the last 5% on the x-axis, if I see, it takes longer with Felix. Is that, first of all, am I reading that correctly?
I think so. I think it takes long for both frameworks. It can be like that. If you, and we are not showing, like this is only the first maybe 4 hours of tuning. If you stretch that more, you will also see that answer will take long for the last few percents, because it is like that in the search space. Most of the programs are decent performance, but only a few of them are very good.
Hi, Alex from Qualcomm. I was curious how you seed the search, because in especially Halide, there are a lot of completely disjoint scheduling opportunities you can have. For instance, differences in tail case handling if you want to do redundant recomputation, or alternatively overcompute internally. How do you sort of choose a starting point and pick between orthogonal or maybe mutually exclusive options?
Ah, I see. This is a question that I cannot fully answer in just 1 minute.
Okay.
But like, you have time to check in our paper, but I will give you an review. So we do actually, there is something in Felix that is similar to what answer does, that is sketch. So we have a few sketch-like things. Let's say we have a few different symbolic schedule for the same operator, and then we optimize on them at the same time to make sure that we can cover different parts of the search space where you have different sequences of transformations.
Okay, thank you.
Okay, let's thank you, the speaker again. So while the speaker is setting up, the next speaker is Chunwei Xia, and he's a postdoc from University of Leeds, and he will be presenting optimizing deep learning inference via global analysis and tensor expressions.
Okay, good. Hello, everyone. My name is Chunwei. I'm so glad to be here to introduce you our work about optimizing deep learning inference via global analysis and tensor expressions. This paper is a collaborative effort between University of Leeds, Institute of Computing Technology, University of Aberdeen, and the Awake Research. Okay. A linear model is typically expressed as a computation graph written by TensorFlow or PyTorch. To further reduce the inference latency and reduce the programmers developing operators burden, researchers propose that deep learning compilers like TVM, XLA, and Triton. The deep learning compiler compiles the operators into binary executable kernels, and then these kernels are launched on the NVIDIA's GPU or Google's TPU. Okay, as the left figure shows, the high bandwidth memory's access latency on the NVIDIA GPU is around 10 times higher compared with the on-chip buffer, for example, the L1 cache, and 100 times higher compared with the registers. Deep learning compiler can help reduce the inference latency by operator fusion, as the right figure shows. And here are some state-of-the-art works, and one of the representative fusion work is DRAM fusion. The DRAM fusion classifies the operators into 5 categories and fills the operators by the predefined rules, as the figure shows. However, current deep learning compilers typically fills the operators one by one, as the left figure shows. And this approach is hard to extend to new operators, and furthermore, often stuck in local optimizations, which misses the data reuse opportunities. Okay, to further reduce the inference latency, we would keep as much as data on the chip buffer to maximize the data reuse. And secondly, as we fuse more and more operators, we want to make sure the fused kernel can still be fit on the hardware. And third, we want a fully automated compiler that can automatically fuse the operators and generate the code without predefined rules or the heuristics. So our ultimate goal is that if we can compile a whole DRAM model into a single kernel to reduce the kernel launch overhead and enable more cross-operator optimizations. So here we propose a DRAM compiler that adopts a top-down approach we named as SOFO. The compiler first pre-processes the whole DRAM model as a single kernel. Then it globally analyzes the data reuse opportunities based on the tensor expressions, which means the tensor expression is as the intermediate representation. And after that, it will check if the whole model can be fit on the hardware, and it will try to it will split if it cannot fit on the hardware, and then it will do the automatic transformation on the tensor expression subprograms. Okay, so we utilize the tensor expression to encode the data flow information of operators and tensors, because tensor expression offers concise semantics and allowing us to translate the complex task of analyzing and optimizing the operators into a more manageable problem of analyzing the mathematical expressions. So here is an example of a MATLAB operator. And from the tensor expression, we can get the input-output tensors shape, the parallel accesses, the reduction accesses, and the fine-grained data dependencies between the output tensor C and the input tensor A and B. Okay, to this end, we introduce 3 new mechanisms. The first is a tensor expression-based globally analysis module to globally analyze the data reuse opportunities and the fine-grained data dependencies. And secondly, a resource-aware graph partitioning. And thirdly, a semantic preserving transformation approach that uses the affine transformations to simplify the tensor expression programs and generate the kernel for them. Okay, first let's talk about the global analysis. The lower the tensor expression program is passed to the compiler's analysis module. The module performs 2-level analysis. The first level is the tensor level. First, it will check the compute intensity of the tensor expression, get the optimized schedule from the underlying scheduler, like the answer or meta scheduler. Then it seeks two data reuse opportunities. The first is a temporal reuse, which means one operator is accessed later by another, which means one tensor is accessed by another operator later. And secondly, is a spatial reuse, which means one tensor is consumed by a branch of operators that without dependencies between them, so we can increase the parallelism. Secondly, we analyze the fine-grained element-wise dependency. Our key observation is that the intra-tensor expression data dependency can fall into two categories. The first is one relies on one, which means the output tensor's one element only relies on one input tensor's one element. And secondly, for the tensor expressions with reduction accesses, the output tensor's one element relies on all the elements of all the reduction accesses. And with this observation, we can greatly simplify the dependency analysis processes compared with the source code level or operator level fusion approaches. Okay, secondly is the graph partitioning, because the compiler tried to generate a large kernel to maximize the data reuse. However, to use the global synchronization, we need to make sure that the block count limit cannot exceed the maximum block count limit for the GPU and in the mean, as well as for the shared memory. So, for example, assume we have a GPU with 8 MB shared memory, and for the first part, it requires 2 blocks, and for each of the blocks requires 4 MB shared memory. And for the second one, it has 8 blocks, with each block requires 1 MB shared memory. And the GPU has total 8 MB shared memory. So if we fuse them together, we need 32 MB shared memory. So we cannot fit on the hardware, and we need to split it. So after split the whole tensor expression program, it becomes the tensor subprogram, and the tensor subprogram serves as the fundamental unit for the high-level transformations and the backend code generation, which means for each tensor subprogram, it generates one kernel. And as for the candidate partitioning points, we only consider the compute-intensive tensor expression, as typically the compute-intensive tensor expression consumes more shared memory compared with the memory-intensive tensor expression. Last, then it looks at the opportunity to automatically transform the tensor expressions to improve the performance for each tensor subprogram. So the compiler supports both horizontal transformation and the vertical transformation. For the horizontal transformation, it transforms a branch of tensor expressions into one tensor expression to increase the parallelism. And for the vertical transformation with one relies on one dependency, it will automatically transform the tensor expressions into one to reuse the data on the registers. And for the one relies on many tensors, it will try to reuse data on the on-chip buffer. Okay. To this end, the compiler first transforms all the one relies on one tensor expressions by applying the index mapping functions from the child tensor expression to the parent tensor expression. It then applies the index mapping functions, and finally it automatically creates a single semantic preserving tensor expression. Okay, it also supports the post-optimization. We can, if we fuse the operators into a single kernel, we can pipeline the instructions across the operators. So for more details, you can refer to our paper. And our evaluation platform is a GPU server with 40 gigabytes NVIDIA A100 GPU, and we compare our compiler with strong baselines, including Answer, TensorRT, Apollo, XLA, etc. And we also evaluated the compiler on 6 representative DeepMind workloads ranging from ResNext to the BERT and LSTM. We first present the overall results of our compiler, and we can see that our compiler significantly outperforms other schemes across the evaluated models. And this figure reports for the impact of individual transformations on the inference time reduction. Okay. And our horizontal and vertical transformation can significantly reduce the inference latency. And here we conduct a study on the LSTM model. And for the most performant baseline, the runner generates 200 around 200 kernels, and we generate only 1 kernel for the whole LSTM model. And we can see the DRAM bias load from the global memory significantly reduced, and the pipeline utilization is also increased. Okay, in conclusion, we proposed a compiler that globally analyzes and the tensor expression and automatically transform them. That's all. Thank you.
Thanks for the talk. I was curious, how large were the models that you were testing on relative to the capacity of the GPUs you're dealing with?
It's a very good question. We only test the model that is small. The largest one, I think, is in transformer. It's about, for example, several hundreds millibyte parameters. We didn't test on the large language models.
Okay.
Yeah.
Do you think that has any impact on the necessity or the value of Fusion for your work as opposed to other models that might saturate the machine more without Fusion?
Yes, I think for the large language models, the matrix multiplication, the Fusion, the impact of Fusion would be small because the matrix multiplication dominates the inference time. But for the decoder, which means it's matrix vector multiplication, the Fusion scheme, I think is still can significantly reduce the latency.
Got it. Thanks.
Okay. Thank you.
Hi, thanks for the talk. This is Shrikant from Microsoft. My question was, how much control does the user have in terms of modifying the thread block sizes or enabling custom operations with your system and the compiler?
Sorry, do you mean the users have control on the operator implementation?
Yeah, operator implementation and basically distribution of the work across CTAs and sizing the CTAs themselves.
Okay, I think the front users have they did not need to control the implementation. They just need to provide the tensor expression, which is a mathematical expression. Then the compiler will automatically generate the code without any human efforts.
But as a user, will I have control over that? If I want to change it, can I change that?
Change what? Sorry.
Change the thread block dimensions, the number of warps in the CTA or the shared memory that is being consumed by each CTA.
Okay, that's a good question. Currently, we rely on the underlying scheduler, like the Answer or Map scheduler, to get the optimized tile size and the number of thread blocks. So currently, users have no control on this detailed implementation. It relies on the underlying scheduler.
Got it. Thank you.
Okay, thank you.
Yes, thank you, the speaker again. By the way, there are a few empty chairs here for people who are standing back there. Don't feel shy to come over.
Oh, there's no audio coming from that.
Okay, for the next speaker.
Oh. All right.
All right, so the next speaker, we have Jason Ansel, the tech lead from PyTorch compiler team from Meta, and he's will be talking about PyTorch too.
So the user-facing feature in PyTorch 2 is pretty simple and easy to understand. It's torch.compile. So you take your PyTorch model that's written for PyTorch eco mode, you call torch.compile on it, and you get a faster version of that model that behaves the same as the user There's lots of different options. Under the hood, we have more than 100 configuration flags. But we package up some configuration flags with a number of different modes. So one interesting mode is called max auto-tune mode, where we start doing some auto-tuning. This isn't TVM style auto-tuning that takes 5 hours. When we talk about auto-tuning, we're talking about like 5 seconds, not 5 hours. You know, this is per kernel, and so the number of kernels adds up. So this can basically trade off compile time for performance. We also have a reduced overhead mode, which helps for small models. A lot of models in other papers are more micro benchmarks, and for micro benchmarks, it's really important to enable CUDA graphs because those are basically entirely overhead bound, and CUDA graphs really lowers overhead for and you can also act in a different backend. And so the default backend, which is on here, is called Torch Conductor. But there are more than a dozen backends available for PyTorch, both in the PyTorch repository and available open source. And you can pass it in a custom backend. And one really unique thing that we can do is it's really making it easy to find a custom backend for Torch.compile. So you can basically just define a Python function which takes in a graph and some example inputs. I have one here that's called my compiler. For illustration purposes, it just prints out the graph that it's given. And then you could pass your compiler as the backend equal argument to torch.compile. And as torch.compile just in time compile the Python code, it'll produce graph fragments. And it'll call the my compiler once for each of these graph fragments. So for this example, it produces these 3 graphs. And this makes it really easy to prototype backend for PyTorch. And so the front end for Torch Compile is called Torch Dynamo. And the way Torch Dynamo works is it's a just-in-time compiler for CPython. And we modify the way the CPython interpreter works. So every time CPython is going to evaluate a frame of bytecode, rather than interpreting that frame of Python bytecode using PyVal from default, what we do is Torch Dynamo takes control, and it does a symbolic analysis based on the real runtime inputs. And this symbolic analysis operates bytecode by bytecode, and it simulates the behavior of what executing that Python bytecode would do in order to extract a graph of PyTorch operations, which we can pass to a user-defined compiler. That user-defined compiler is going to return an optimized callable, which is called a function. And we transform the Python bytecode into a new Python bytecode, which then calls the results of this user-defined compiler. And one of the really great things about this approach is PyTorch is an extremely flexible language, and it allows you to do arbitrary Python things. And most AI compiler backends don't support all of Python. And so the way we do this is that anything that the backend compiler doesn't support, we just leave as Python bytecode. And because we're a Python bytecode to Python bytecode transpiler, it is really easy to support all of Python. And because we can just leave anything that we don't support in Python bytecode and interpret it using the real CPython runtime. This gives a great amount of flexibility in PyTorch 2 compared to most other AI compilers. So next I'm going to talk about Torch Inductor, which is the default backend for Torch compile, and how motivate how Torch Inductor works. I'm going to first start out with some of the principles that motivated this design. So the first principle is we want something that's PyTorch native. And so PyTorch has a lot of abstractions in it, which are different from other frameworks. Most notably, we have user visible stride and data pointers, but there's also many other differences that give PyTorch its flexibility that you spoke about. And we wanted a backend compiler that shared very similar abstractions to PyTorch in order to support all the features that PyTorch provides. Next, we wanted a compiler with Python first. And so we actually implemented Torch Inductor entirely in Python, or nearly entirely in Python. And we think this is a huge advantage because across machine learning, most users of PyTorch know Python a lot better than they know C++. And in PyTorch, we see a lot more active contribution to the Python parts of PyTorch, and very little community contribution to C++ parts of PyTorch. And so by implementing our compiler in Python, our compiler is way more hackable by our users. They can go in and make changes, and they can also understand what's going on. And we think that this hackability and community contribution is really valuable. Next is breadth first. So there's a lot of compilers out there that really focus on just one or two models. And if you're only compiling one or two models, you don't need a compiler. You can just hand optimize that one model. And so we really wanted to focus on the hard stuff first, and make sure that we're building a compiler that can scale to hundreds or basically the entire ecosystem of PyTorch models, which is pretty massive. So next, I want to talk about three different technologies that make Torch Inductor unique. And so the first one is a defined by line loop level IR. And what this means is that our compiler IR representation actually contains within it Python functions that have the full power of the Python language embedded in its compiler IR. And the big advantage of this is it makes it really easy to write low rates from PyTorch into Torch Inductor's IR. And this is really important because one of the big bottlenecks that have made it difficult to write compiler to PyTorch is PyTorch has thousands of programs. And if you have a really difficult to use compiler IR, you'll get stuck just implementing low rates. And so by using the full power of Python in our compiler's IR, we were able to very rapidly support large subsets or large fractions of the PyTorch language. Next is dynamic shapes and strides. So another thing that makes PyTorch really unique is how well it supports dynamism. And this was something that we really wanted to build into our design from the ground up. And so we used SymPy, which is a symbolic math library, to reason about dynamic shapes and strides and make sure that our support for dynamism is industry-leading. Next, we wanted to reuse state-of-the-art languages. So we took inspiration from our users. We said, okay, when PyTorch users are optimizing PyTorch programs, what do they use to write really fast kernels and squeeze out the most performance that they can out of their hardware? And what we see is it's most often training for GPUs and C++ for CPUs. And so Torch Inductor generates both of these languages as it comes. A little bit of an aside about what is training, if you haven't heard about it. Although I think it's been that's more widely known now. That is that trends in new DSL for programming GPUs. The way to think about it is it's higher level than CUDA. These are programming at the SM level rather than the trend level. But it's lower level than most pre-existing DSLs. And what's really great is it strikes this balance where it's really easy to write performance competitive code with an order of magnitude less effort than it would take. So here are some performance results. So these performance results are on an NVIDIA A100 doing both training and inference. And what we're reporting here is speedups over PyTorch eager mode. So 1x here is PyTorch eager mode, and higher is better. And we're comparing across 3 different benchmark suites, where each benchmark suite consists of more than 50 models. These are full-size models, and we're taking the geo-mean performance across each benchmark suite and showing it. So we have TorchBench, which is primarily research models. We have Hugging Face, which is primarily transformer models. And then we have TIM, which is mostly vision models. And we can see that Performance varies across these three different benchmark suites, but on average, torch convection is significantly faster than the other approaches. We compare to 6 other AI compilers. The first 4 are industry compilers, which have varying levels of performance. Then the last 2 are research compilers that we're comparing to. So let's zoom in a little bit and see, how is this performance distributed? And so what we've done is we're not just looking at inference only. The training version of the graph is in the paper. And we are looking at the cumulative distribution function of speedups. So in here, the x-axis is the speedup, and the y-axis is the number of models that achieve that speedup. So you can see that torch conductor on lots of models is delivering between 10x and and down speedups. Where when you reach the 4x point, torch conductor is generating more than a 4x speedup on around 40 models, while most other compilers aren't generating that level of speedup on any models. And then if you look at the other backends, you can see that XLA is generating speedups between 3x and 1x on lots of models, but it's also generating slowdown in other models. For NNC and NV user, most of their speedups are clustered around 1x. And the reason for this is that they actually use PyTorch mode and only compile subsections of the model. And then Onyx, CVM, and HitEd are both primarily generating slowdowns compared to PyTorch. So this is an ablation study where we're trying to say, okay, where are the speedups in torch inductor coming from? And the way we measure this is we take our compiler and we measure the speedup it has with an optimization, with all optimizations enabled. Then one by one, we disable specific optimizations and we see how fast the torch inductors generate. And the intuition here is that if you remove an optimization and it causes a bigger slowdown, then that optimization is more important. And I won't go into the details of what all these optimizations means. You can read that in the paper. But what you'll notice from this is that the vast majority of the speedups are coming from fusion and inlining. And fusion and inlining are both different ways to basically combine kernels together, which reduces memory traffic because you can pass data between kernels and registers rather than needing to round trip through memory. And so this is the last slide, and I'll close with a call to action to use our benchmarks. And so looking at benchmarking in academic papers, I think things are in a really sad state. We're not doing a good job at benchmarking. And there's a few different problems with academic paper benchmarking. So one is not enough benchmarks. And often when we are doing benchmarks, they're micro benchmarks, not real benchmarks. Or resident merge are very much overstudied. Second, what we see is often academic papers will claim these enormous speedups, and we'll go and try them, and they won't reproduce. We can't read, and often the most common thing here is just misconfigurations. And so I would say use our benchmarks and do that.
Thanks for the talk. This is Wang from Amazon. I have 2 questions. One is I'm a big fan of the work, but what do you think is the major miss of the current version, the current PyTorch 2.0 work? And or another way, how do you envision your major future work? And sorry, I finished that. Second, at Amazon, we have our own accelerator, which uses XLA as the graph level exploration, and we write our own Tensor compiler. And how can we make best use of your work? Thanks.
Yeah, so there's what are new research areas? So for one thing that we're spending a lot of time on is improving distributed and really getting out to larger scales. I think there's still actually a lot of room for additional speedups and additional optimizations. And there's a lot of work going on there. And and in terms of using our PyTorch, there's lots of different ways you can integrate with PyTorch. You can integrate at the FX graph level, which I showed an example of here. You can also integrate at the torsion vector level, where you could go from torsion vectors IR to the to a language. And I know that there's a language similar to Triton or AWS hardware that you could potentially lower from torsion vector to that. Then you can also add a backend to Triton. So Triton supports AMD GPUs, Intel GPUs, NVIDIA GPUs, Meta's custom silicon MTIA. And so we're seeing a lot of success of people integrating with PyTorch at the Triton level. That's a particularly common with that integration.
Oh, it's a very great work, and I think it will benefit millions of people. And my question is, why did you choose the Triton as the default backend? So, what do you think its advantage over the XLA or TVM? And okay, and my second question is, how to extend the Torch Dynamo backend to new compilers like XLA or TensorRT or other deep learning compilers? Thank you.
Yes. Both TensorRT and XLA backends for Torch Dynamo in PyTorch. So you can just use those. In terms of comparing Triton versus XLA versus TVM, I think XLA is really good on TPUs, but up until recently there hasn't really been enough investment in XLA for GPUs and CPUs. In terms of TVM, I think TVM pretty far away from state of the art. And what you'll find is TVM works really great on microbenchmarks. And the reason why it works really good on microbenchmarks is the search space is really small, and you can also iterate and search in that space really well. So if you have a graph of like 40 nodes, TVM looks great. But then if you pass a full-size model to TVM with 4,000 nodes in it, the problem is the search space is exponential, and it just completely fails. And we get cases where we run the TVM auto-tuner for more than a week, and it's failed to achieve even the performance of the TVM auto-tuner. And so I think this is a case where you see all these research papers about like 10x speed up on TVM, and usually what it is it's going from like 5x versus the state of the art to 2x versus the state of the art. And so I think that's a case where we need to benchmark better.
Okay, thank you.
All right, I think we ran out of time. Let's take the rest offline. So thank you to the speaker again. So for the next speaker, we have Muyan Xu from UIUC, who will be talking about kernel orchestration with Torch.
Okay, I push it up. And hi everyone, I'm Yuan Hu. I'm a first-year PhD student at UIUC. And today I'm going to present this paper, Optimal Kernel Orchestration for TensorFlow Compilation with Torch. And by the way, I don't know if they delivered it just after PyTorch 2. Is it because we are calling Torch? I'm not sure. All right. And high-performance execution of deep neural networks is very critical for many machine learning applications. And from all kinds of machine learning front ends, DLN or tensor program can be represented as a computation graph, where each edge represents a tensor and each node represents a tensor operator. But the problem comes to how to efficiently execute this computation graph on modern hardware accelerators, where the computation is always organized as kernels. A kernel is a function which will simultaneously execute multiple hardware threads in an SPMD fashion. So this is our newly identified kernel orchestration problem: how to map the DN operators to GPU kernels. And Previously, kernel orchestration is solved by operator fusion. For example, on this subgraph of conv, b, and value, previous operator fusion framework will have some predefined rules to fuse those three operators into one big kernel. However, let's look into this subgraph on SecFormer. Operator fusion will use 4 kernels actually. The first, div kernel. The second, softmax kernel. Third, add and transpose kernel, and finally the metamo kernel. The only fusion did here is add and transpose. So there are 2 main limitations of previous operator fusion work. First, operator fusion is always greedy and based on many predefined rules, which needs much human effort and is also locally optimized. And second, there are some very sophisticated operators, and it is very challenging to have them executed efficiently in only one kernel, such as softmax. Softmax includes the calculation of element-wise, reduce, and broadcast. They have different level of parallelism, and it is very hard to put all of them in one single kernel. So based on those observations, our first motivation is to decompose those sophisticated operators into finer-grained ones with unified level of parallelism. For example, this is how we can decompose softmax into 4 finer-grained operators: element-wise exponential, reduce sum, broadcast, and element-wise division. The key benefit of this decomposition is that we can do more graph-level transformations and fuse different parts of softmax with other parts of the graph. Here, UXP can be fused with the division, and pad can be fused with add and transpose. The reduce is merged with metamo, and the softmax kernel become a much cheaper one. So the calculation of softmax can be distributed into all the other kernels in the subgraph. All right, and this is an overview for the Coach compiler. First, we have an input tensor program, and we'll do some graph partitioning to get several subgraphs. And first, Coach will apply operator fusion to decompose it into a primitive graph and use some graph optimizer to do primitive graph level transformations. And after that is the second part, kernel orchestration. First, Coach will identify all the candidate kernels and use a kernel orchestration optimizer to find the optimal kernel execution strategy. And in the end, we'll generate the optimized executable. So first part, operator fusion. Coach applies operator fusion to decouple each tensor operator into 4 classes of tensor algebra primitives, and each of the primitives will carry basic algebra calculation with a unified degree of parallelism and data access pattern. And based on the relationship between the input and the output elements, we have first element-wise primitives, including element-wise, element-wise div, and some activation functions. For the reduce and broadcast primitives, we have reduce sum, max pull, broadcast, and so on. For layer transformation primitives, we have transpose, slice, concat. And finally, the linear transformation primitives. This will include all the compute-intensive operators like convolution, gem, and batch gem. And after the operator fusion, the computation graph will be featured into a primitive graph. And here's an example on the softmax attention subgraph. There are 2 main benefits of operator fusion. First, as we mentioned in the motivation part, operator fusion can unlock more primitive graph level transformation opportunities that cannot be found on the original computation graph level. We can leverage an off-the-shelf graph optimizer to do more transformations on the primitive graph. And on the softmax attention primitive graph, Tensor can do the illustrated transformations to fuse the reduced primitive in softmax with metamo. And after the primitive graph transformations, the second benefit is that operator fusion will enable more flexible kernel orchestration. Here on this subgraph, Coach can use 4 kernels to finish the execution. Compared with the original graph, here, kernel 1, since the only fuse of div is the EXP, so latency will be similar with the original div. And similarly, kernel 2 will have same latency or similar latency with transpose. And kernel 3 matter more. This is the almost same matter more with the previous matter more. And for the fourth kernel, this one is much cheaper than our softmax. So this is why we can get some speed up on the subgraph. But here comes the question. How can we find this optimal kernel mapping strategy? And so our solution is to formalize the kernel orchestration problem into a binary linear programming. Use the candidate kernels to cover the whole primitive graph. A candidate kernel is a subgraph that can be computed in one kernel. For example, on this QKV subgraph after operator fusion and primitive graph level transformation, we have 21 candidate kernel subgraphs in total. And after identifying all of them, we will formalize the BLP problem to select the kernels to cover the whole primitive graph. And the objective is to minimize the overall latency sum of the selected kernels. So let's talk about the constraint of our BLP. Actually, the only constraint is the dependency. If a candidate kernel is selected, all of its inputs should be prepared. For example, in the last slide, we have an optimal strategy when to choose P5, the matmil, as one of its kernel. Since matmil have two inputs, so both of those two inputs should be prepared by some previous kernels, input 1 by this kernel and input 2 by this kernel. And since dependency is the only constraint, our selected kernels can overlap with each other. For example, those three kernels share a same primitive P1, and P1 is calculated 3 times in all of the kernels. But if we don't do redundant computing, we need 4 kernels to finish the computation on this subgraph. So here, redundant computing helps us save 1 kernel and achieve a trade-off. We can sacrifice more computation to achieve less data movement, since the compute capability is much more powerful than memory bandwidth on modern GPUs. And such strategy can be naturally found by the BLP solver. And here are more details of our binary linear programming problem. And you may think that the number of candidate kernels will be a very large number, since it could be exponential with the number of primitives. But actually, since most of the deep neural networks, they are very deep and thin, and we can prove that the complexity of candidate kernels can be roughly simplified as quadratic with the depth of the primitive graph. And such simplification is also adopted in some previous work. And for the profiling and cogent of each kernel, we use a simple heuristics. For compute-bound kernels, since it will include a linear transformation primitive like convolution with very complicated schedule, and we will directly use vendor libraries like cuDNN and cuBLAS to do the cogent and profiling. But for man-bound kernels, since the schedule is much simpler, we will just use TVM. And it only takes 10 seconds on average for each kernel to finish the profiling and cogent. Also, this process is independent with each other for each kernel, so the profiling and cogent of each kernel can be easily parallelized on a multi-GPU system. Okay, and now let's do some recap to compare Coach with operator fusion. Operator fusion has bad granularity. It suffers from bad granularity and cannot deal with sophisticated operators very well. But Coach first applies operator fusion to ensure a unified granularity. And operator fusion is based on human heuristics and is always locally optimal. But Coach formalizes a BLP problem, so it is always globally optimal. And operator fusion can only do a many-to-one mapping from the operators to the kernels. It is actually a subset of the kernel orchestration mapping space. And for Coach, we can do many-to-many mapping. It will have more flexible kernel orchestration. And finally, let's look into the evaluation part. We have evaluated Coach on NVIDIA V100 GPUs and A100 GPUs, including CUDA core experiments and Tensor core experiments. And our benchmark models include CNNs like Candy, YellowV4, YellowX, also transformers, including SecFormer and efficient VIT. Our baselines are PyTorch 2, TVM, and TensorRT. So for the end-to-end results, Torch can achieve up to 1.7x speedup within 12 hours of tuning time. And this figure shows our numbers on A100. And let's do some case study. First, we did an adaptation study of operator fission, which means that we only do the operator fission and feed the primitive graph to TensorRT and let TensorRT to decide the optimal kernel orchestration strategy. So we disable our BLP. And only with operator fission, we can have 1.24x speedup on the SIG-formal case. And the second case study is on the BLP. This is a tension block of efficient VIT, and here's a comparison between TensorRT's strategy and Torch strategy. As you can see, TensorRT uses 12 kernels in total, but Torch only uses 7 kernels. And for kernel 2, kernel 3, and kernel 4, they have overlap, and the shape transformation and shape is executed 3 times in those 3 kernels. And we can have 3.29x speed up on this case. And finally, to conclude, we have identified a new problem kernel orchestration. We first apply operator fusion and we enable more fusion opportunities. And after that, we formalize a BLP to find the optimal strategy. And our code will be available on GitHub, and thanks for listening. Questions are welcome.
Yeah, so I was a little surprised by these PyTorch 2 results, and we actually we have a number of these same backends that we've run against both in our paper and outside our paper, and also some of these same models we've actually run. So I actually when I looked in our data, and our data actually directly conflicts with your data by more than an order of magnitude, and so it's clear that both can't be right. And so my first thought was like, oh, there must be like some misconfiguration. Maybe you're running a smaller version of the model, not using coup de grace, or I was trying to think that. So I went to your artifact evaluation to try to basically go and actually reproduce using your code to try to figure out, okay, why is there an order of magnitude difference between our results? Okay. And I noticed that in your artifact evaluation, you only published 2 Onyx models. You didn't share the PyTorch versions or any of the code you used to run PyTorch. So my question is that can you open source that code so that we can try to directly reproduce your results?
Yes, I think our code will be available soon on GitHub, and maybe there's a possible reason for the mismatch of the results, since maybe we'll use an early version of PyTorch 2, and when we run Torch to compile, and it gives some errors on some models. So like EuroX, it give a very slow number for PyTorch 2. I think there's something possible reason.
We have historical dashboard data that's actually updated every single night. And like, there's no point in our history where of like going back to even before the release of PyTorch 2 where these numbers would make sense.
Yeah, we can try it out.
Hi, I'm Gina from Stanford, and I had 2 questions. One was like, I think you have like in your primitive graph nodes like matrix multiply, but actually we could express matrix multiply using add, multiply, and reduce. But I'm assuming like, I think you could also like, when you have a mapmul, you could use your mapmul node, but it's also possible to express it using add, multiply, and reduce. Like, how do you make this decision? And also, do you think the primitive graph design is something tied down to your targeting hardware like GPUs? Because like you have higher level nodes like matrix multiply, but I think like that's also something tied to because you have a specialized core like Tensor core that could do matrix multiply. So I think like I was wondering like for your high level nodes you have in your primitive graph, is that something kind of tightly coupled with the targeting hardware that you want to run it on?
I think it's not coupled with the hardware, since our operator fusion is only considered the relationship between the input and the output. It's all just on the tensor algebra level. And I think our work can be also extended to TPUs, since all of the modern higher accelerators will use kernel as an abstraction. So it is possible and very interesting the results on the TPU experiments.
Okay. Also, just for the first question, like how do you make the decision of like whether you want to decompose and matrix multiply into smaller units like add, multiply, reduce, or do you want to keep it as high level like you have in the like mapmul? Because I think you have both granularities in your primitive graph.
Yeah, I think this is one part that is manually designed in our system. Now we only have linear transformation primitive, and matrix multiplication will be the least granularity, and we will not decompose it more. But it is possible to do more exploration, try to decompose the linear transformation operators.
Okay, it's just more. So I think the reason why you don't want to actually decompose is something because you have an accelerator unit that could do maybe.
Oh, yeah,
multiple-
yeah,
so
yeah.
that was the reason of like you
Yeah,
have
yeah,
different granularities in your primitive graph, but
Yeah.
the reason why you don't is it looks like something that's kind of related to your targeting hardware.
yeah, I think that's true.
Okay.
Okay.
All right. Well, thank you everyone for attending and for so many questions. Let's thank you the speaker again.